Hello, good afternoon. Good afternoon. Am I audible?
Yes, sir.
I think last class, whether we solved these examples.
So the screen is not presented.
Yeah, no, it's present. No, I think is it all visible?
Yes, sir.
Whether we solved this example. Yes or no?
Yes, sir.
Yes, sir.
Okay. Topic. Let me start from here itself. So, in the previous class, we saw we discussed related to topics related to LED and its construction and also varieties. The next slide, I'll be telling you about the differences between those two. Well, let us discuss about the advantages of LED. So, the advantages of LED, wherein, as you all know, the design is very simple, and it is easy of manufacture. Easy of manufacture. It's easy of manufacture. Easy of manufacture. So manufacturing these LEDs is very simple, and so it can be manufactured in arrays like Yeah, what it is in arrays and pin strips and all those things you are seeing. Next is simple system integration. So it gets easily integrated to any circuits. That is what the simple system integration. So it doesn't require any complicated circuits in order to get assembled with the other circuits. So it is the integration to any system very simple. The cost base, as you all know, it is very low and it is highly reliable. Highly reliable. So we can rely much on this LED. But at the same time, any device for that matter, it will be having advantages. At the same time, it will be having a disadvantages. So the disadvantages of your LED are the refraction of light at semiconductor air interface. So this refraction of light, it takes place between this semiconductor and the air interface. The average lifetime of a radiative recombination is only a few nanoseconds. Nanoseconds. Hence, the the lifetime of your any radiative recombination. Basically, the principle you know, it's a recombination that takes place due to which photons will be liberated. That is what we call. So here it is all. It will be in nanoseconds. Hence, your modulation bandwidth it will be limited to only few megahertz. Only it will be in terms of hundreds of megahertz, not in terms of gigahertz. That is the thing. And also low coupling efficiency. The efficiency in order to couple. So because as you all know in the previous we have discussed about the spectrum, the radiation pattern of your LED. It is wide compared to your laser direct. That is what we had discussed in the previous class. Hence, the coupling efficiency is very less since it's a radiative pattern or the radiation pattern is very large compared to your laser diode or any other sources. So here most of the this thing will be lost. Hence, the coupling will be low, very low. Large chromatic dispersion. So as you all see, the radiation pattern is more, hence dispersion will be more, and due to which uh, the losses will be. You all can note down this thing, which we have already discussed. So the radiative and non-radiative recombination lifetimes of minority carriers in the active region of a double heterojunction LEDs are 60 nanoseconds and 90 nanoseconds respectively. So you're telling that the recombination lifetime of your minority carrier, that too in the active region of a double heterojunction LED. So it is not a single, it's a double heterojunction LED. It is 60 nanoseconds as well as 90 nanoseconds. So what he has told here, he has the question it's being asked to calculate or to determine the total carrier recombination lifetime. Total carrier recombination lifetime and optical power generated internally if the peak emission wavelength of silicon is 870 nanometer. Peak emission wavelength SI is of silicon is 870 nanometer and the drive current is 40 milliamps. So which is the formula it is being used to calculate the total carrier recombination time? First of all, I think is the question clear? Someone should tell me something. You people have to reply me whether you understood the question or not. Hello? Am I audible? First of all, am I audible? Am I audible or not? Hello. Yes, no, okay. Yes, sir. See, if you people text me, really I can't see because my window will be presenting the slides wherein I will be not able to see your messages. So you people please do voice message. Drop a voice message. Okay. You can instead of texting me, you can directly answer. So it's given lambda it is 870 nanometer. So here you have the peak emission wavelength is 870, whereas the recombination time it is 60 lifetime. See the radiative tau r and the non-radiative tau nr, it is given non-radiative. So the radiative recombination lifetime is 60 nanosecond, and the non-radiative recombination lifetime is tau nr, which is equal to 90 nanoseconds. So here tau r is equal to 60 nanoseconds and tau nr is equal to 90 nanoseconds. And the drive current is 40 milliamps. 40 milliamps. So what you are supposed to calculate? You are supposed to calculate the total carrier recombination lifetime and optical power generated. So the formula is just like this. Sorry. So the total recombination lifetime, just it's a substitution 1 by tau, which is equal to 1 by tau r plus 1 by tau nr. So the total recombination time will be equal to tau will be equal to 5400 divided by 150. Okay, are you able to follow me?
Yes, sir.
Yeah. The total carrier recombination time, or you can say the bulk recombination time also be in other words, it can also be called as total recombination carrier recombination or the bulk recombination time. So the tau will be given by 1 by tau is equal to 1 by tau r, that is a tau radiation, plus 1 by tau nr, that is a non-radiation. So 1 by tau is equal to, you will be substituting 1 by 60 nanoseconds and 1 by 90 nanoseconds. If you substitute, what is the answer that you are going to get? What's the answer you're going to get? Any answers?
Sir, tau is equal to 36.
Tau is equal to 36. What is the unit? What will be the unit? It is a 45. 20, yeah. 55 is a 35, I think. 54 divided by 1.5. 36, right?
Sir, 36. Sir,
Yes, very
unit
good.
ಏನು ಗೊತ್ತಾಗ್ತಿಲ್ಲ sir.
Yeah, 36 nanoseconds. So it will be in nanoseconds because it is tau r is in nanoseconds and 90, that is the tau nr is also in nanoseconds. So finally, tau will be in terms of nanoseconds only. Fine. Now, next, what is given in the question? In the question, it has been asked to calculate the optical power generated internally. See, power generated internally. So the formula P internally. So internal optical power P int is equal to N, that is efficiency integral into HCI by Q lambda. That is what we have discussed in the previous class. This formula I think we have discussed in the previous class. If you substitute all these things, so in efficiency will be equal to tau by tau r, which you already know in the previous these things. Okay, we have already in the previous class we have discussed that one, right? So what would be the answer? Sorry, here Okay, in the calculation, tau by tau r is wrong. That is 36 by 60. Hello? Please make a correction.
Yes.
P internal is equal to 36 by 60. Tau, just now you have calculated here. It is 36 nanoseconds. 60 nanoseconds. Tau r. So nanosecond cancels. So 36 by 60. 6 by 10. 6 by 10. Okay. Then H you know, C you know, I drive current 0.04 milliamps, that is 40 milliamps. So 1.602 into 10 power minus 19, that is the Q. Okay, lambda it is given 870 nanometer or 87 micrometer. What will be the answer? What's the answer?
Sir, 0.034.
Ah, something. What is the value of the rate?
Sir, 0.03424 watts, sir.
Any others? Okay, otherwise you people calculate. Okay, we'll move on to next problem. Shall I? Smoke. Smoke. The last hour of the class. So most of you are on a sleeping mode. Huh? We'll move on to next problem. Please note down a double heterojunction indium gallium arsenide phosphide LED, which is operating at 1310 nanometer, has radiative and non-radiative recombination times of 30 and 100 nanoseconds. 30 and 100 nanoseconds. The drive current is 40 milliamps. Calculate the bulk recombination time, internal quantum efficiency, internal power level. So given 1310, tau r is 30 nanoseconds, tau nr is equal to 100 nanoseconds, I is 40 milliamps. So here the notation is wrong, just I have taken screenshots. Please don't note down like this. This is equal to again. So here also we will be calculating like this. So this is the bulk recombination time n 1 by tau. 1 by tau is equal to 1 by tau r plus 1 by n tau nr. Tau nr. If you substitute that is 1 by 30 plus 1 by 100 nanoseconds, you'll be getting somewhere around 23.1. 07 only here it is given. Okay. 23.07. And the internal quantum efficiency formula is n internal, that is efficiency int equal to tau by tau nr. If you substitute, you'll be getting 0.769. Internal power level, which will be equal to n int, that is an efficiency, into HCI by Q lambda. It's just like the previous problem. What is the answer? What is internal power? What is internal power level? Hello. What is the internal power level? Whether you got. Hello. Ready at that. ಅದೇ ನಾನು ಕ್ಲಾಸಲ್ಲಿದ್ದೆ ಬರ್ತೀನಿ.
Sir, 0.0291 watts, sir.
Shreyas, that will be equal to again 0.02913 is nothing but 29.13 milliwatt.
Yes, sir. Yes, sir.
Yes. So the answer is correct. So we'll wind up here. In the next class, we'll take up laser diodes. Okay. Now I am leaving just because, as you all know, our VC cremation is last rites will be held now. So is next to my road. So I am going there. So please, sorry. Okay. We'll continue in the next class. Thank you all.